we will be studying 5 models, okay? 4 of them are exponential, and 1 of them is logarithmic. Now, we will not graph these, but we will be familiar with what each graph looks like, okay? We will also apply this information today to solving word problems. Contain your excitement, okay? So it shouldn't be too difficult, but it will be somewhat challenging today. Your heading for today is exponential and logarithmic models, okay? Write that down in your notes if you would, please. Lesson 7.5, and be sure and include today's date. I'll pause a second while you copy that down. Exponential and logarithmic models, lesson 7.5, and be sure and include today's date. Okay, let's continue on now. Let's start off by looking at these 5 models and what their graphs look like. I don't believe you need to take notes on this information, but rather go ahead and get your books out, please, quickly, and turn your books to page 496, and you will see all of this information that I'm about ready to show you. You will want to write down the models in your notes. Okay, so you will want to write down the models, just not the graphs. Okay, the graphs are right there on page 496 for you. Okay, so quickly turn to page 496, and we're going to move on. Now, here are the 5 models we're going to look at today. Okay, now the first thing I want you to do is in your notes, I want you to write down this. I want you to write the words exponential growth model. Would you please copy that in your notes? Now I'm going to go fast, so you're probably going to have Mrs. Gallen, or whoever the supervising teacher is, pause the video a lot today, okay? But I want you to copy that in your notes, and then copy this model down, exponential growth model, and then write this. Okay, so there we go. Now look, guys, A is a number, E is a number. Of course, E is kind of like pi. I mean, pi is a number, but it's the same number. Well, E is a number also, we know that. Remember, E is something like, what is it, 2.718281,828, something like that, okay? So E is a number, A is a number, and B is a number. And notice, write this down also, please, students, it's so important. A is greater than 0, and B is greater than 0. When you have this scenario right here, you have an exponential growth model. Got it? Okay, now here's an example of an exponential growth equation. Here's an example right here. Write this down, please. There we go. And 2 would be your what? Your A. And 3 would be your B. Okay, so there you go. Exponential growth model. Now, very quickly, I want to show you what the graph looks like, and you'll see it there in your book, okay? Here's an exponential growth model, and it makes sense, guys. Look, notice how it's growing as you go further to the right. Notice the graph is growing. It's getting higher and higher and higher and higher, and that's always what an exponential growth model will look like when you graph it, okay? All right, let's take a look at model number 2, okay? Model number 2. Hold on one second. There we go. And there we go, and here we go. Okay, in your notes, I want you to write down exponential decay model. Okay, please copy that in your notes. Okay, after you've written that in your notes, then go ahead and write down the model in your notes. Write down y equals a e negative bx, and then put down a is greater than 0 and b is greater than 0. Please write all this down. Now you're probably thinking, Mr. Earhart, they made a mistake. Look, b is negative, b should be less than 0. No, it's right. Okay, it's correct. It's totally fine like this. There's a negative sign here, but with b right here, what they're saying is basically this. You have a negative sign and then a positive b. Okay, something like this real quick. Y equals a e negative, and then a 3, and then an x like that, okay? So b would be 3, which is greater than 0, and you still have your negative sign right here, okay? All right, so anyways, copy this model down, and here's an example for you. Okay, students, so here we go. Here's your example. An example of an exponential decay model, or an example of an exponential decay equation would be this right let's see, 5e to the negative 4x. So a would be what? 5, and b would be what? Not negative 4. B would be positive 4, okay? Now, you know what the graph looks like of this? The graph of this looks like this. There it is, okay? See how? No, wrong one. Sorry, guys. Your old teacher's getting old here. Sorry about that. Here it is. Let's see how it's decaying. Look how it's decaying, guys. Look, as you go to the right on the x-axis, and you get further and further to the right, the graph is going down, 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 down. And yes, it's going to bottom out, and yes, it will never cross the x-axis, but it's still getting lower and lower and lower. Okay, just slower and slower and slower. But that would be an example of an exponential decay model. Okay, exponential decay model. Okay, let's continue on to model number 3. Okay, model number 3, the Gaussian model. Okay, so in your notes, go ahead and write down Gaussian model. Okay, copy that down, please. Gaussian model. And then go ahead and write down this model right here in your notes, please. Y equals A, E, and then for the exponent, negative, parentheses, x minus b. Notice this, students. Quantity squared all over c, okay? And notice that A has to be greater than 0. So there you go. There's your Gaussian model. No, I really don't have a lot to say about this except that A's a number, B's a number, C's a number, E's a number. Okay, so here's an example of a Gaussian model. Here it is. Copy this down. Here's the model. There's the model. And now here's an example of an equation that is a Gaussian equation. Here it is. Y equals, and for A we'll put a 1. And then for my exponent up here I'll put negative parentheses x minus 4 quantity squared all over c. We'll call c 6. So there you go. There's an example of a Gaussian equation. Okay? Alright, here's what the graph would look like. Alright, and you don't need to copy the graph. The graph is in your book. Okay? Now later on we're going to take some notes on this. And don't write this down now. But we call this a bell-shaped curve. Bell-shaped curve, but don't write that down now. We're going to talk about that later, okay? But here's the general form of what the graph looks like right here. And you see this a lot in statistics, okay? Statistics, okay? Not an easy word to say. Statistics. All right, now go ahead in your notes and write down this. Write down logistic growth model. Okay, copy those words down in your notes. Logistic growth model. And then copy this model in your notes. Y equals A over 1 plus BE to the negative RX. Okay, copy that in your notes, please. There's the model, and go ahead and copy this down too. Logistic growth model, and here's the model right here. Copy that down. A is greater than 0. Okay, students, now look, there's the model, okay? Here's an example of a logistic growth equation, okay? Oh, by the way, notice A's a number, B's a number, okay? R's a number, E's a number, okay? So here we go. Here's an example of a logistic equation. Y equals, for A, I'll put a 1. For B, I'll put a 2. For R, I'll put a 3. There we go. There is my logistic growth equation like that. Okay? So not too difficult. I'm not going to make you memorize these. You're more than welcome to have all of these on a cheat sheet for your quizzes or tests. I don't mind that at all, okay? But be familiar with these, okay? Alright, moving on. Let's take a look at what the graph would look like, okay? The graph of a logistic growth function. Just like that. And notice, please, students, do notice something. It is not a straight line. It looks like it's not. Okay, it is not a straight line. It's supposed to come up, have a little bit of a bend here, and then flatten back out again like that. asymptotes. Did you get that? There are two horizontal asymptotes on a logistic growth model. Okay? And of course, where those asymptotes are depends on the equation itself, okay? I'm not going to get into that now. I would like to. It's pretty cool, actually, but I'm not going to get into that. But logistic growth models, graphs, have two horizontal asymptotes, okay? And then it's not a straight line. It looks like it, but it's not supposed to be a straight line, okay? There's a little bit of a curve, and it would continue to curve and bottom out like that, and like that also, okay? So there is the graph of your logistic growth model. Now, we're not going to spend a lot of time on number 5 because we already know number 5. We've dealt with number 5 over and over, okay? In your notes, go ahead and write down logistic growth models. Write that down. And then write these two models if you would, please. But really, that's all we're going to do, guys. I mean, we've dealt with these already. Y equals a plus b natural log of x, and y equals a plus b common log or log base 10 of x. Okay, there we go. An example. Well, you know an example. We've graphed a bunch of these already, and we've solved equations like this. Y equals 2 plus 3 natural log of x, or y equals 2 plus 3 logarithm of x. So there's two examples of a natural and a common logarithmic equation or function, okay? And we know what their graphs look like already, okay? We know what their graphs look like. Here we go. I got both of them here. We know this. Guys, we learned this a long time ago. Look, when you graph a logarithmic equation, there will always be a vertical asymptote. Remember? Come on, we know that. You take the argument and you set equal to 0 and solve, and that gives you the vertical asymptote. Over here, vertical asymptote. Take the argument. I can't draw a very straight line, can I? Here's your vertical asymptote. Alright, and here's your argument. Take your argument, set equal to 0 and solve, and that's how you get your vertical asymptote. We've learned all that, okay? So there's the 5 models we're going to use today as we work on these word problems, okay? And some of the word problems will be easy, some of them will be challenging. Please keep your books open. We're going to use your books a lot today, okay? So without any hesitation and with great excitement, let's go ahead and jump into this, okay? Here we go. Let's spend the rest of the time looking at word problems. Here we go. Okay, page 497, example number 1. So go ahead and turn your books to page 497, example number 1. And students, let's go ahead and get started with this, okay? Here we go. Now, there's no need for you to copy the problem down. It's right there in your book. If I were you, I would just write in your notes, page 497, example 1, okay? Now here's what it says. The world population in millions from 95 to 2003 is shown in the table. And of course, in your books there, you see the table. I don't have that up here, it's no big deal. Here's the model, this exponential growth model. Here's your A. Here's your B. Okay, this exponential growth model is a model that approximates the population. Okay, P is the population in millions. Okay, and T equals 5 represents 1995. So where T is right here. Okay, I'm gonna write the model really big so we can see it here a lot better. And of course, you have it in your books also, where T is right here. If I were to put a 5 and then type this whole thing in my calculator, I would get out the population for when T equals 5. And when T equals 5, what year is that? 1995. So I would know the population in 1995. Let's pretend I put a 10 in there. Okay, a 10. And got out a number. Well, that would be the population for what year? Well, 5 years later, so 2000. Do you see that? Okay. T equals 5 is 1995. T equals 6 would be 1996. T equals 7 would be 1997. T equals 10 would be the year 2000. So I can put a number in and get out the population in a certain given year. Okay. Now, according to, hold on 1 second, please. Okay. According to this model, when will the world population reach 6 billion? Now, please let me help you. First of all, it's a model that's in what? Millions, yet they're giving us a number that's in what? Billions. So let's let's relax here, okay? Now, watch this. The number a billion is what? What does a billion look like? Well, that's a million. And that's a billion. Got it. How many zeros do you have in a billion? 3, 6, 9. So when it says 6.8 billion, you know what that means? That just means move the decimal. How many places? 9. Because how many zeros do you have here? 9. So move the decimal 9 places. So 1, and then 2, 3, 4, 5, 6, 7, 8, 9. So you would have a comma here, a comma here, and a comma here. So 6.8 billion really means 6 billion 800 million. Okay? Got it. So there we go. Okay? So when it says 6.8 billion, that really means this number right here. Got it? Alright, now let's continue on. Here's what they're asking us. Look, in what year, when will the world population reach this? So here's my model right here. Got it? P equals 5,340 e to the 0.012922t. Okay? So there it is. Now, they're saying, hey, put this number in for p and solve for t. But the problem is, if I'm going to put in 6.8 billion in this equation, I have to do it so that it's in millions. And right now, this number right here is in what? Billions. So how many millions are in a billion? Okay, now watch. It's not that hard to figure out. Watch this. In the number a million, how many zeros do I have? 6. So just take the decimal and move it 6 places, and it'll be written in billions, or in millions, okay? Let me go over that again. This is 6 billion 800 million, or in other words, it's 6.8 billion. But we have to get it put in here so it's in millions. Whatever number you put in for p has to be in millions. So if I want to write this in millions, how many zeros are in a million? 6. So move the decimal 6 places. So 1, 2, 3, 4, 5, 6. The decimal's right here. So really, 6 billion 800 million is the same thing as just saying 6,800 what? Million. Now, if you need to go back and rewind the video and watch that again, feel free to do that. But that is how you would go from, that is how you would do all of this, okay? So make sure you understand this. So for p right here, I'm going to put 6,800 equals 5,340 e to the 0.012922t. We're going to solve for t. Now come on guys, don't panic. You know how to do this, okay? We did a bunch of these before fall break, okay? It's not that hard to do. We're solving for t. It's called an exponential equation. We know how to solve these. First of all, we're going to get the base of the unknown all by itself. So I'm going to divide both sides by 5,340. Okay, so 6,800 divided by 5,340. And when I do that, I'm going to get this right here. Now I'm going to leave a good. I'm going to round it to a pretty long place. 1.273408 equals e to this power right here. Now, students, remember, if you can write both sides with the same base, you need to do that. We can't write both sides with the same base. There's no way we can do that. This is a base of 1.273408. This is a base of e over here. There's no way. So remember what to do. The base of my unknown is e. So I'm going to take log base e of both sides. Remember, log base e equals sign log base e. And I chose log base e because the base of my unknown is e. Okay? So that's why it's so important you learn this last before fall break. Okay, so I take the log base e of both sides. Now, on the right side, this is easy. Whenever a base matches a base, the entire answer is your exponent, okay? So all of this will come down here. So 0.012 over here, log base e of this is really the exact same thing as natural log of this. So with my calculator, I'm going to type in natural log of 1.273408. And I'm going to get this out right here. 0.241696771. Okay. Now divide both sides of your equation by 0.012922. And you're going to get this right here, 18.7. Okay. Now, that doesn't help. That tells us how many years, but they want to know when it's going to happen. Okay, so remember, 1995. Went with what year? 5. So that means 2000 would go with what year? Or excuse me, the year 2000 would go with what number? 10. So the year 2005 would go with what number? 15. So add 3, we have 18. Add 3. The year 2008 would go with number 18. Now it's 18.7, so it's not quite to 19, which is 2009. So the answer is somewhere during, here's your answer, somewhere during 2008, okay, is when the population will hit 6.8 billion. Okay? Alright, that's it, guys. Moving on. We have 4 of these, 4 more word problems to do today, okay? Here we go. Okay, in your notes, go ahead and write down page 498, example number 2. Okay, 498, example number 2. Okay, in a research experiment, a population of fruit flies is increasing according to the law of, look guys, exponential growth. Okay? After 2 days, there's 100 flies. After 4 days, there's 300 flies. How many flies will there be after 5 days? Now, in the last problem we did, they gave us a model, so it wasn't too hard to predict something. Here, they don't give us the model, so, yep, you guessed it, we gotta find the model, okay? So, here we go. We're going to use our exponential growth models, which is this right here. Okay, so there we go. So my one equation would look like this. If I put in 2 for x, I get out 100 for my flies. So 100 for y equals there we go. Where the y is, I put 100. Where the x is, I put 2. Okay, and b2 is the same thing as 2b. I'm just going to go ahead and put 2b. Now, my other equation will look like this. After 4 days, there were 300 flies. So 300 equals A, E. And then I would have, let's see, B times 4. And of course, B times 4 is just 4B. Now, look what you have. Guys, students, listen, in order for you to write the model that you need to predict how many flies there'll be in 5 days, you have to find A and B. Once you know A and B, you can write your model, okay? So we got to find A and B. So how many unknowns do I have in this equation? 2, A and B. How many unknowns do I have in this equation? 2, A and B. Well, you learned this in Algebra 2. When you have 2 unknowns and 2 equations, you can solve them using substitution. So watch carefully what I'm going to do here, okay? I'm going to take my equation over here. I'm going to solve it for A, okay? So I'm going to divide both sides by e to the 2b, e to the 2b. Now here's why I'm going to do that. Watch. These cancel, and A equals 100 over e to the 2b. Now, why didn't you solve for b, Mr. Earhart? Well, I could have, but it is easier, you'll see, to solve for a, okay? Now, look what a equals. A equals 100 over e to the 2b power. So I come to this equation, and I put that in for a. So now I have this. 2b. That's for a. Okay, so there's a right here. And now bring down the rest of your equation, e to the 4b. Now look, this whole equation now has only b's in it. So I can solve this for b. Now you're probably thinking, Mr. Arrow, you're crazy. That's going to be really hard to do. It's not that bad, okay? It's not that good either, but it's not that bad, all right? So watch. All right, here we go. Okay, let's solve this for b. Now look, don't panic. Think, okay? I used to have a boss that said, don't work harder, think harder, okay? So think for a second. Now first of all, if at all possible, I want to simplify this right side over here, okay? So put this over 1. And now you have now you have this times this over here, okay? And one thing I just noticed, students, be really careful, it's my fault. This right here looks like e to this whole power. And I'm so sorry, that's not what it's supposed to be. If you look back here on this page here, it's 100 divided by e to this power. So be really careful there, okay? All right, here we go. So I have 100 over e to the 2b power, okay? And I have a fraction over here. So look what you can do, guys. Look, watch this. We now have this. We have 300 equals. Remember, we're solving for b. So I have 100 e to the 4b over e to the 2b. Now, students, go back to Algebra 2. Think about this. If I had x to the 4th, if I had 2x to the 4th over 3x squared, like this, you know what to do when you're dividing like bases. You subtract the exponents, okay? So you would have 2 over 3, x to the 4th divided by x squared. 4 minus 2 is 2, so you would write x squared up top. You took the top power minus the bottom power because you had like bases. Well, guys, look, it's the same thing over here. Look, you have e to the 4b, e to the 2b, like bases, e and e. So look what you can do here. Subtract your exponents like this. 4b minus 2b. That would give you 4b minus 2b would give you, well, think about it. 4b minus 2b, that would give you 2b. So I have 100 e to the 2b power. Now, if you want to put that whole thing over 1, you can, that's fine, but you don't have to. Now we're looking pretty good. Now just solve for b. So divide by 100, divide by 100. Okay, and we're left with 3 equals e to the 2b. Now you have an exponential equation. There's no way you can write both sides with the same base. There's no way. So what is the base of your unknown? E. So take log base e of both sides. Bring down your 3. Bring down your e to the 2b. Now, log base e of 3 is the same thing as natural log of 3. Over here, whenever your base matches your base, everything's gone except the exponent. So divide both sides by 2, and now we know what b equals. Natural log of 3 divided by 2 equals b. So take your calculators, natural log of 3, enter, divided by 2, enter, and you'll get this. I'm gonna round it to a pretty long place, okay? 0.549306. There's your b. So we know what b is. That's so important. Now, let's go back over here. Remember, we know what a equals. Look in your notes, students. We solve for a. Okay, let's stop. Don't lose sight of the trees for the forest here. Remember, our goal is to predict how many flies there will be after 5 days. Well, there's no way we can here we go. That's not good. So here's B right here. We just found it, okay? Here's A. Look at A, guys, right here. A is 100 over E to the 2 times what power? 2 times B. What's B? 0.54936. So now I can solve for A very quickly. So with my calculator, I'm going to type in all of this here, and I should get approximately 33. Now, if you're struggling, you want to hit E to the 2 times this power and get a number, and then take that number and type in 100 divided by that number, and you should get approximately 33, approximately. So now I know what A is, now I know what B is, so I can write my model, okay? So I'm going to erase everything except for A and B in my model here. Here we go. So there we go. So here's my model. Y equals A. What's A? 33. Then E, and then B to the X. So 0.54936X. We've got our model. We did it. Now we can solve the problem very easily. Okay, look. How many flies will there be after 5 days? So where the X is right here, I'm going to go ahead and put a 5. So go ahead and cross that off. Put parentheses and put a 5. So with your calculator, type this whole expression into your calculator, and you should get out this for an answer. Approximately, not exactly, 514. And there we go. We did it, okay? So a tough problem, not super easy, but that's how you would solve that, okay? All right, let's continue on. Okay, so let's go ahead and continue on. Here we go. Let's take a look here. Okay, let me quickly draw your attention to the bottom of page 498. If you are not on this page, please turn over there now, page 498. I'll pause a second while you do that. Please turn to page 498. Okay, before we start the next word problem, I want to give you a little bit of information about Gaussian models, okay? Oh, I'm sorry, guys, I messed up, sorry. Okay, go back to page 498 at the bottom, okay? Sorry about that. Okay, I want to very quickly point out something to you. In this text, there's going to be some times where we do some, look at the bottom of page 498. They call it carbon dating, okay? Now, carbon dating is going to prove that some things are millions of years old, okay? Millions of years old, and we know that's not true by biblical creation. So all that I want to say is this: don't forget, in times past, there have been scientists who have taken certain objects, okay, and they have already known how old the object was. Maybe it was 40 years old, and they have done they have done carbon dating on it, and the carbon dating showed it to be maybe thousands of years old or something like that, when the scientists knew it was 40. Thus, it is true that carbon dating has been proven false. It is not always accurate. Okay, you need to know that in case you go to a secular university. Okay, carbon dating is not always accurate. And remember from geometry, it only takes one counterexample, okay, only one, to prove a theorem or a property or a conjecture wrong. Okay, you should remember that from geometry last year. Okay, so carbon dating is not accurate all the time. Thus, it cannot be used to prove that certain items are millions of years old. So please understand that if we do some problems in this chapter in which answers are millions of years old, just ignore it. Use the formula they give, and we're going to practice our math, okay? But just want to point that out to you, okay? Before we start the next word problem, I want to give you a little information about Gaussian models, okay? Gaussian models. Please copy this down. First, the graph of a Gaussian model is called a bell-shaped curve. You can probably see that right now, guys, on page 499. Look over at 499, and you'll see a bell-shaped graph, okay? That's called that's a graph of a Gaussian model, and we call this a bell-shaped curve. For obvious reasons, it looks like a bell. Okay, it really does. So make note of that in your notes. Secondly, this model is usually used in statistics. Okay, usually it's used to represent situations that are normally distributed. Now, I'm not going to get into what that means when we say normally distributed. That's a statistic class terminology. But just so you understand, Gaussian models are usually used in statistics. Okay, so make note of that and understand that. Okay, having said that, in your notes, go ahead and write down page 499, example number 3. Page 499, example number 3. Okay, and here we go. Okay, the problem reads as follows. Here we go. Let's see here. In 2001, the SAT math scores for college-bound seniors roughly followed this equation right here. Okay. As long as x was greater than 200 and less than 800. Okay. X is the SAT scores. Sketch the graph. Well, we know it's going to be a bell-shaped graph. I'm not going to make you do any graphing, so I'm not really too worried about the graphing part. However, look at part B. From the graph, estimate the average SAT math score. Now, it is true. Please listen to me, students. Please listen. It is true that if you were to graph this, it would look like this. In fact, you see the graph right there on page 499. The graph would look like this. It is true that the average score would be this high point right here. Okay? So, really, if 200's over here and 800's over here, okay, then it stands to reason the middle, the average would be 500. But here's the problem with that reasoning. You don't, look, listen to me, students. If you did not have that graph in your book for you to look at, you wouldn't know that 200 was over here, and you wouldn't know that 800 was over here. What if the graph looked like this, guys? What if 200 was here on the graph and 800's over here? Okay? Then we got a real problem. There's no way 500's the average. Do you see what I'm saying? So here's how we need to solve this. Please watch carefully. What I'm going to do is I'm going to put 200 into this equation. Now, students, it's really hard to do. Please let me help you. Are you ready? Please let me help you, okay? We're going to put 200 for x right here. See that x right there? Look in your books if you need to, okay? All right. Let me get a drink here real quick. Hold on. Okay, now look, students. We're going to put 200 for x. So with your calculator, type in 200 minus 514, okay? And if you do that correctly, you're going to get negative 314, okay? Everybody do that? Now, take negative 314 to the what power? Second power. Hit enter, okay? And you should get this. Okay? Now, there's a negative sign out front, so now put a negative in front of it. So now we have the whole numerator. What's it divided by? 25,538. So type that in. Go ahead and take negative 98,596 divided by 25,538. Hit enter and you should get this. Negative 3.86076 rounded. Okay, so now you know your whole exponent. So you really have this. You have 0.0035 e to what? To the what power? Negative 3.86076. So with your calculator, type that whole expression in. Okay, right here. Go ahead and type in 0.0035. Go ahead and type that in. then hit e to the x, so second natural log, and this should pop up. And type this in, negative 3.86076. Okay. Enter. And you should get scientific notation 7.36819 times 10 to the negative 5. So move the decimal 5 places to the left, and you should have this 0.00007368. So there we go. So now we're kind of seeing a little bit of where that would be on the graph, okay? Now, let's put in 800, okay? And see what we'll get out. So here we go, okay? Let's do this again. All right. So now I'm going to put in 800 for x. So 800 minus 514. And you should get 286. Okay, and then square that. And when you square that, you should get 81,796. But remember, there's a negative sign here, so put your negative sign, then divide it by 25,538. So divided by and you should get this, students. You should get negative 3.202913 rounded. Okay. Now, look, guys. That means for your now the entire exponent equals this. So now you have this 0.0035 e to the negative 3.202913. So very quickly with my calculator, I'm going to type in 0.0035 and we're going to get this 1.4225 times 10 to the negative 4. So you're really going to get this. You're going to get 0.0014225. Okay? Now, think this through for a second, students. Look, when I'm at 200 here, I'm up 0.00007 over here when I've gone over 800. I'm up higher. This is a bigger number. I'm up 0.0014. So I'm a little higher up, like maybe here. So think about it, guys. To find the average, I really would not want to be at 200, okay? Because 200 is too low down the curve. If I want to find the middle, I'd probably scooch along here to about right here, maybe, I don't know, 220 maybe, okay? And now I'm higher up on the curve, because why would you do that, Mr. Earhart? Here's why I would do that. Students, I want this point here and this point here. If I were to connect them, I want them to be parallel to the x-axis. In other words, I want this point here. I want a point here that's directly across from this point here. So about a point here, maybe right there. So they're directly across. So now I'm more like at about, I don't know, 220 maybe, okay? 225, something like that, okay? So now I can find the average. If I find the average between 225 and 800, okay, so if I do that quickly, what I would come up with would be I got 512.5. Now the book has 514, okay? And I totally get that. It's fine. I would have no problem on a test or a quiz. I would just want to see the work that you had done in which you showed me that you knew to put 200 in and get out a number here, and then put 800 in and get out a number over here, and then, kind of show me that you had estimated here and then found the average, okay? That's all I would really, really want you to do on a problem like this, okay? So not too bad, okay? So the main thing we practiced here was plugging in or substituting numbers into a Gaussian model type of equation, okay? And then interpreting those results, okay? All right, moving on. Okay, now before we solve a word problem, using a logistic growth model, let me first give you some information about this model. Okay, so here we go. First of all, notice this picture at the top of the page. Okay, notice if you look in your books on page 500, notice you'll see this picture right here. Okay, notice you do not need to know. I'm not going to test you on this or this. However, I want to remind you or point out to you once again that a logistic growth model has two horizontal asymptotes, okay? Here and here. And most of them will increase quickly and then level off, decrease quickly, or increase, going left to right, it would be increase quickly and then level off, and then decrease like this and flatten out, okay? And so that's something you need to know about a logistic growth model. Okay, moving on. This graph is called a logistic curve. You need to know that, okay? Also, a logistic curve is also called a sigmoidal curve, okay? A sigmoidal curve. I'm not going to test you on that. You don't have to know that, but I just want you to be familiar with that, okay? So if I use this term or this term here, you'll know what I mean, okay? All right, moving on. Now, in your notes, go ahead and write down page 500, example 4. Page 500, example 4, okay? On a college campus, there are 5,000 students, okay? One student returns from vacation with a flu virus. The spread of the virus is modeled by this, okay? Where y is the total number of students infected after t days. The college will cancel when there's 40% or more of the students are infected, okay? So with that in mind, first of all, part A, how many students are infected after 5 days? So where the t is, I'm going to put a 5. Now it really shouldn't be too hard to do, students, okay? I mean, you have 0.8, negative 0.8 times 5, which gives you negative 4, okay? So really I have now this. I have 5,000 over 1 plus 4,999 e to the negative 4. So I can type this whole thing here into my calculator very quickly, and I would get this out. 2,000. So when there are 2,000 students absent, they'll cancel classes. Got it? Okay, so here we go. We have to take this model here, and where the y is, we're no longer putting something in for t. We're now putting something in for y, and we're going to solve for t. This will not be easy, so please pay attention. 2,000 in for y, because that's how many students that need to be absent. 40% in order for the college to close. So 2,000 equals 5,000 over. That right there. Now, don't panic. Oh my goodness, Mr. Earhart, this is crazy. No, it's not. Don't panic. Simplify, simplify. First of all, we could multiply both sides by this denominator to get rid of our fraction. But look at that denominator. That's a wicked long, okay? How about this? 2,000 is really over what number? 1. I can flip one side, okay, like this, as long as I flip the other side. So if I flip the left side, I have 1 over 2,000. If I flip this side, I would have 1 plus 4,999 e to the negative 0.8t over 5,000. Now let's go ahead and get a new page up here. And now let's solve this. Now look, students, what is your denominator? 2,000. What is your denominator? 5,000. So I'm going to multiply both sides by 10,000. Okay, that would give me 5,000 over here. And over here it would give me 2,000 times this whole expression here. Okay, now I would divide both sides by 2,000, so I would then have this. 2.5, 5,000 divided by 2,000 is 2.5. I'm going to divide this side by 2,000 and divide this side by 2,000, okay? So I'm left with 2.5 equals this. Now, if you bring the 1 over and make it a negative 1, what you want to do, students, you're solving for t, so you want to get the unknown and its base all by itself. So I want to bring the 1 over, make it negative, then divide both sides by 4,999. Okay, now if you do that correctly, you're going to come up with, let me do it real quick here, 2.5 minus 1 divided by 4,999 would give you 0.0003006 equals e to the negative 0.8t. Now remember, you have a base e, okay? So I'm going to take log base e of both sides. Okay? So I'm going to bring this down here if there's room. So log base e of this number equals log base e of this whole side right here, okay? Now, the right side's easy. Whenever your base matches your base, you're left with the exponent. So negative 0.8t. Over here, I'm going to type this in my calculator. Log base e is really the natural log of this decimal. So natural log of 0.0003006. Enter. I'm getting this right here. Negative 8.1115. 8.13. I'm just going to say 10. Okay, approximately 10. So approximately after 10 days, there will be 2006 students, which would then cause the college to cancel classes. Okay, approximately. Guys, we're doing some really good math. This is tough. It's not easy, okay? But we're solving some difficult equations. Okay, last but not least, now we're not going to do A, B, and C. We're just going to do A to save time because A, B, and C are 110% identical. You do them the exact same way, okay? So here we go. Page 501, example number 5. On the Richter scale, the magnitude R of an earthquake of intensity I is given by this model here, okay? And students, sorry, I had to take a break there. I'm back now. Okay, look. So the magnitude R of an earthquake of intensity I is given by this, where I subscript 0 equals 1. That's the minimum intensity used for comparison. In other words, you have to have a starting point in which you compare the intensity to something. Okay? Now, stop and listen to me. This is the formula used to find the Richter scale. You know, you guys have heard in the news before, oh, California had an earthquake that registered 8.3 on a Richter scale, you know. Well, here's the formula or the model they use to find that, okay? We're going to go backwards today. Now, listen, they're not going to ask us to find the Richter scale, the magnitude on the Richter scale. They're going to give us the Richter scale, the magnitude, and they want us to find the intensities per unit. Okay, now intensity is a measure of the wavelength of the earthquake. So we're going to use this model here. They're going to give us R. We're going to put a number in for R, and then we're going to solve for I. It's really not that hard, guys. It's pretty simple. So we're ending on a pretty simple problem. So here we go. Here's my model. I over. Now look, guys. I subscript 0 right here. It's 1 equals 1. So I'm just going to put a 1 here. Okay, there we go. Now, R is 8.3, so for R, I'm going to put 8.3. And of course, base 10 is just a common log. And I over 1 is just I. So guys, that's it. Look what we're doing. We're solving a simple logarithmic equation. Guys, what is your base right here? Remember how you can write logarithmic equations exponentially? So write this exponentially. It would be 10 to the 8.3 power equals I. And that's it. So with a calculator, go ahead and type in 10 to the 8.3, and you will get 199,526,231 for your answer. Okay? So here we go. 199,526,231. Now I'm not sure why the answer in the book, why they rounded. Maybe it says to round somewhere, I'm not sure. I'm trying to see. But anyways, there's the answer. Okay? So you just found the intensity, intensity per unit of area for the earthquake that was in Japan. Okay? The Richter scale was an 8.3 and 8.3, and you found the intensities per unit of area. And there it is right there. So those are pretty simple. So what have we done today, students, other than probably confuse you and give you a headache? What we have done is we're learning how to take models, exponential, specific, logarithmic, and exponential models, and we're learning to put numbers into them and solve and use them to then get